This is Jack Jackson. We're going to talk today about continuity and differentiability and how they relate to each other. So recall that the definition of a derivative of a function at a point A is the limit of a difference quotient. So f prime of A is defined to be the limit as h approaches 0 of f of A plus h minus f of A over h. So notice, for us to even think about possibility of the derivative to be defined at the point, f of A, the function, must be defined there in order for the difference quotient to be defined in order for us to be able to take the limit. So notice that the function must exist in order for it to be differentiable. So if the function does not exist, then the derivative does not exist. So differentiability, by differentiability, what we mean is the derivative is defined at the point. Okay? Let me go ahead and add that to the notes. Differentiability means at a point means that the derivative is defined at that x value. Okay, at A in this particular case. So, differentiability implies that the function exists. Well, what about continuity? Continuity, you remember that for a function to be continuous, the function had to exist, but there was a little bit more. The limit had to exist, and they had to be equal to each other. Does differentiability imply continuity? So to investigate that, we're going to look at an example here, and I have somewhere, if I can find it, a GeoGebra sketch that I want to look at. And here it is. Let's take a look at it. And in this particular picture, I wanted to look at something, a function which is not differentiable at a point. Now, the point exists there, but it's not continuous at that point. So in this case, it's sort of left continuous, but not right continuous. In other words, the limit from the left of this f of x as x approaches A is f of A, and there is a point there, but the limit from the right is not. So the limit from the right is down here, I don't know, whatever this is. Actually, I can move it. Let's say it's looks like that's close to 1, and this one is close to, like, we can put x at A at 7, and put that, oh, it looks like it's close to 3. Okay? But anyway, whatever it is. Now, let's look at some difference quotients. Okay, so what we're looking at here is the slope of these secant lines. And over here, you can see these points. Let me make this the point 7. See if I can make it the point 7, 3. And I can't exactly, but anyway, there it is. And here's another point nearby. Now we have some different slopes, but look what happens as we let this come in. What happens to these tangent lines, secant lines? They're getting closer and closer to a vertical line, and remember the vertical line doesn't have a slope. The slope is undefined. And anytime we're going to have a break in the graph, at least from one side, we're going to get this. Now, on the other side, if we come in from the other side, I don't know if I can do it. So if we pick a point over here and do the point here, the secant lines are all the same, so they're all the same as whatever the slope of this little line segment, this half of a line, this ray is. Okay, whatever slope that is, you get the same difference quotient on this side. The limit on that side is that, and there's sort of a legitimate tangent line from that side, but there's not a legitimate tangent line really at the point, because from the right side we don't get, it's not approaching a specific tangent line. In particular, it's approaching actually a vertical line, and so it's undefined there for the slope. So notice that this is going to happen anytime we have a discontinuity. We're going to have this same problem. There's going to be a break somehow, and when you try to come in at least from one side to that point, you're going to get a vertical line that you're approaching at least from one side. So, what does that tell us? Conclusion. The conclusion is, there's the picture again, the conclusion is that when you have a discontinuity at a point, it has to be non-differentiable at that point. So a function must be continuous at x equals a for the derivative to exist. So in other words, if there's a discontinuity to x equals a, then the derivative is undefined at x equals a. So another way to say that is differentiability at a point implies continuity at that point. If it is differentiable, then it must be continuous. If it's not continuous, then it's not differentiable at that point. Well, now then, what about the converse of that? Does continuity at a point imply differentiability? Maybe continuity and differentiability are the same concepts. If it's always continuous, so we know that if it's every time it's differentiable, it's continuous. What if every time it's continuous, it's differentiable? Is that true or is that not true? Let's look at an example there. Okay, and the easiest example I know to consider, one of the things that might happen, is this function right here. Y equals absolute value of x. So f of x equals absolute value of x. Now remember, absolute value of x is x when x is positive, and the opposite of x when x is negative. Okay, so let me actually, okay. And so that means if you take 2 points on this side, it's part of a line with slope 1, and 2 points on this side, it's on a line with slope -1. So notice that this is continuous everywhere. It's one connected piece. Everywhere on this graph, the function value exists and the limit exists, and they are the same. So this is a continuous function everywhere. But let's look at the most interesting point here, which is at the origin, where we have a vertex or a sharp corner. It's actually a vertex of this. The shape is actually a right angle. 2 rays with a common endpoint, and it's a right angle. What happens right at the origin? Well, if we take 0 as our a value and take a point to the right, our secant line is actually this line here where y equals x extends on down, and so the slope is 1. And we let that h approach 0 from the right, all those secant lines are the same. They all have slope 1, so the limit from the right is 1. On the other hand, if we take a point on the left side and take it along with the origin, that gets this line here, which has a slope of -1, and let h approach 0 from the left side, all those slopes have -1. So that tells us that the limit from the right is 1, and actually I can work it out here. F of 0 plus h minus f of 0 over h. Take the limit as h approaches 0 from the right, that should say. Okay, let me fix that. Oh, that is right there. This didn't look right. For some reason it's not looking right here. Okay, I can see it now. I just couldn't see it from my angle. That's a plus there. So that's from the right side. So when you're looking at this, f of 0 plus h is, if h is positive, well, of course, 0 plus h is h. F of h for a positive h is just the absolute value of h, which is h. And the absolute value of 0 is 0. Let me actually write that step in. So, let's see here. So this is, the function there is the absolute value function. Okay, and since h is positive, the absolute value of h is h, the absolute value of 0, of course, is always 0. H minus 0 is 0. H over h is 1, and the limit as h approaches 0 of 1 is 1. And so that says the limit from the right is 1. We made a geometric argument a while ago, and this is the algebraic argument for the same thing. Now, what if we take the limit from the left? We have f of 0 plus h minus f of 0. 0 plus h again is h. So this looks just like before. And then let me put in this step here. This should say, both of these again should be absolute values, because that's what the function is. But when h is a negative number, see h is to the left of 0, the absolute value of h is the opposite of h. And so this becomes minus h over h, which is negative 1, and that limit is negative 1. So again, in this picture, we do see the algebraic version here and in the pictorial or graphic version up above. So either way, what do we know? We know the left and right limits are not the same, so the limit here, which actually defines the derivative, that limit does not exist. So it's not differentiable at the origin. So differentiability and continuity are not the same. This was an example of a function, look back here at the picture, is an example of a function which was continuous at the origin but not differentiable there. And basically what was the thing that caused us the problem? What caused us the problem was the sharp corner. So we have that abrupt change of direction there, the sharp corner, and that's maybe continuous like it is here, but not differentiable. So differentiability implies continuity, but continuity does not imply differentiability. There's another type of thing that could happen where it can be continuous but not differentiable. And to illustrate that, let's consider the function f of x equals x to the 1/3, or in other words, the cube root of x. And if I graph that, it looks like this graph that you see right here. Now again, this is continuous everywhere, and let's look at what happens at the origin. So at the origin, as we look at secant lines coming through here, whether we're coming from the right or the left, there is a well-defined tangent line there. That tangent line is the y-axis. You see that? Well, whereas before we didn't really have a well-defined tangent line here, there's sort of two candidates. From the left, the tangent line ought to be the line y equals x if you're coming from the right. If you're coming from the left, it ought to have been y equals minus x. There's not a single well-defined tangent line there. In this case, there is a well-defined tangent line. So those limit of the secant lines does have a limit. It's the tangent line. But the problem is that tangent line doesn't have a slope. That tangent line is a vertical line, and vertical lines do not have a slope. The slope is undefined. So there's two things that could happen where you could be continuous at a point but not differentiable. One is that you could have a sharp corner. Another one is that it does look like a line, but that line is vertical, and so we have that. So again, the function has no single well-defined tangent line, such as when there's a sharp corner in the graph at the point. That's like the y equals absolute value of x. There's lots of other things that look kind of like that. The function has a single well-defined tangent line at that point, but the line is vertical. If either one of these things happen, it could be continuous but not differentiable. So now if we look at this sort of gives us a Venn diagram that gives us a relationship among these different sets of functions. So remember, if we take all the functions that are defined at x equals a, that's this blue outer group. Within that, you have a subset of those that are all the functions that are continuous at x equals a. So if it's continuous at a, it has to be defined there, but there are some functions which are defined there that are not continuous at that point. And then within that, you got another subset, the set of all functions which are differentiable at x equals a, and those functions are not only, they're continuous and they're defined at that point, okay, but there's some in the pink that are continuous at the point but not differentiable there, and again the blue out here, there's some that are defined there but neither continuous nor differentiable. Alright, related to this idea is local linearity. What happens when we zoom in on a graph? So here's our good old friend y equals x squared, this blue line here, And here I've graphed the tangent line specifically when we're talking at the point 3, 9. Okay? So at 3, 9, I figured out what the derivative is and found the slope, and then used my slope and my point to find the point-slope form of this line, and I graphed it. And so that you can see that's the tangent line. Now if you look at the big picture, this graph here is curved, this one's straight. They don't look really that much alike. But now let's start to zoom in. So we zoom in on this part of the graph here. Now the graph looks like it's disconnected just because you can't see the part where it's connected off screen. But again, I want to look at this part right in here. Notice that the derivative, the tangent line and the function actually are pretty close together for this part right in here. As they get further away from of course they touch exactly at the point 3, 9. As we get away from the point 3, 9, they're not the same graph, but as we get further away they start to deviate a little bit, like you can see them separating here at the bottom. But what if we zoom in a bit closer? Wow, look at that. Or even more so, look at this one over here. At some point, you can't even tell the difference visually between the derivative, the tangent line, and the original function. Okay, this always happens if you have differentiable functions. Okay, when you zoom in close to them, they look like the tangent line. So they look like a non-vertical, because remember they have tangent lines which are not vertical. So they look like a non-vertical line if you zoom in close enough to them. So if you zoom in near the point AF of A, the graph looks more and more like the tangent line. Sometimes we call this feature local linearity. So if one zooms in close enough to a point AF of A on a graph of a function which is differentiable at that point, then the graph looks like a non-vertical line, in other words, a tangent line. Now, notice that that's not going to happen up here where we had something that was not differentiable. If we zoom in on this vertex right here, it's going to be a sharp corner no matter how much you zoom in on it. If you zoom in here on the origin on this one, it will look like a line, but that line will be a vertical line. If you zoom in here, it looks like a non-vertical line. In fact, if we zoom in at the big difference between, say, y equals x squared and y equals absolute value of x is y equals x squared is differentiable everywhere. If we zoom in, it looks more and more like a line. And even if we zoom in right here at the origin, it's going to flatten out and look like a horizontal line, the horizontal tangent line. Right? Whereas, so that bottom kind of smooths out and flattens out as you zoom in and zoom in and zoom in and zoom in, whereas the absolute value of x, when you zoom in and zoom in and zoom in, you still see a sharp corner. So we say that differentiable functions are smooth. That's a way of describing them, describing the graph. Continuous functions are connected. Differentiable functions are smooth. So it actually, nice smooth thing there. So if you rub your hand across this, you shouldn't get hurt. Whereas if you go across maybe this absolute value of x up here, you might prick your finger because that's a sharp corner, right? So, but differentiable functions are not like that. They're smooth. So they look like locally linear. So one of the things that we can do is we can use the tangent line to approximate a curve sufficiently near the point of tangency. We'll look at that a little bit later. Or we can use the graph of the curve to approximate the tangent line near the point. The two are very close together. Now, it's only exactly at the point of tangency, but it can be very close for nearby points. And of course, as you move away, those two are no longer quite so close together. So right in here, extremely close together, extremely close here. A little further as we get away here, you can see it. And of course, here quite a ways away. Over here, when you're quite a ways away from the point of tangency. Okay, so bottom line, what did we learn in this video? We learned that differentiability implies continuity, implies the function exists at that point. So we have the functions, we have all functions. There's special ones that are defined at a particular point. Within that, there's a more special class that are continuous at that point. Within that, there's a more special class that are differentiable at that point. So for the derivative to exist at the point, it must be defined there and it must be continuous there. but that's not enough. It needs a little bit more. What does it have to be? It actually has to not have any sharp corners like this. It also has to not have a vertical tangent line there. Okay? In fact, when you zoom in close, it's going to look like a straight line, like the tangent line. So it is locally linear. So we can use linear functions, which are the simplest kind of function, really, to approximate just about any kind of function that's differentiable. So most well-behaved functions are differentiable, and so we can approximate them with straight lines, at least over a short period.